responses available. Or the other question can be how can the optimal seagrass meadow be determined regarding the management strategy and also the climate change process. And as I already mentioned, the need of regarding the management strategy and also is crucial because after this question, in order to provide the solution, we need to make another change, especially within the coastal erosion for the beach. In order to make that, several experiments have been done. And what we have developed now is an emulator of the coastal erosion which is a fully AI-driven emulator, which means that instead of using all these model chain up to the X-pitch morphodynamical model, which is computational, really demanding. It requires GPU time. It requires integrations for days or weeks. We use here the AI-driven approach, which integrates all these elements and provides solution within few minutes up to the hours. And this is very effective for the nature-based because it reduces the computational cost a lot and enhances the visibility of different what-if scenarios. Because the what-if scenarios, they are connected with many simulations. These simulations, they require a lot of computational time. And you can see here, for the example, how this work provided maps for erosion that is done, and the computational time reduced compared to the standard approach is 94%, which it matters. This is why the AI-driven technology can really enhance the efficiency for predicting the bed level change, for predicting how the morphodynamic develops with or without nature-based solutions and provide a powerful tool for the decision making. Another example for the AI enhanced technology here is for providing the risk analysis maps. When we have our data and information, this information has to be transferred in the easiest, most way to the stakeholders to be used. And here's also where the AI technology is used with the data program. And I will end my presentation with providing here an example of how this digital twin of Ocean 2 works for the nature-based solution and how really the user can select the different what-if scenarios for making its own decision for using the mangroves or seagrass for protecting its own cost. And here this is a video with audio. Can you please now is the audio active? We have the audio.
The Hydrodynamics and Data Assimilation team at Heriot, KSD, is working on implementing the use of nature-based solutions in a variety.
Another example for the AI enhanced technology here is for providing the risk analysis maps. When we have our data and information, this information.
The Hydrodynamics and Data Assimilation team at Heriot, KSD, is working on implementing the use of nature-based solutions in a variety of use cases. Nearly 40% of the world's population lives within 100 kilometers of the coast. Coastal vulnerabilities such as erosion, flooding, and biodiversity loss are getting worse with climate change. Strategies to protect the coast usually focus on physical barriers such as seawalls. We can use nature-based solutions as a coastal protection strategy, like planting seagrass meadows. Vegetation like seagrass at the coast can reduce erosion and wave heights. It is also a carbon sink, helping climate mitigation efforts. Thanks to our Edito digital twin of the ocean application, for example, we can figure out the conditions that make nature-based solutions an option for coastal protection. We use modern technology to combine advanced coastal models with real-life observations, for example, from the Edito data lake, and artificial intelligence augmentation. This gives us the power to explore the best ways to use coastal vegetation and predict coastal risks. This can be customized to your needs, whether that's seagrass meadows in the Wadden and Black Seas or mangrove forests off the coast of Ghana. We can create priority risk maps and generate knowledge of where nature-based solutions work best, which is applied as part of the Edito and Focus projects. This empowers decision makers working to protect our coasts. With our tool, you can create different scenarios to see the impact of nature-based solutions like coastal vegetation. Taking the example of seagrass, you can set up your own scenario to explore its impact on wave heights and erosion risk. Within 100 kilometers of the coast. Coastal vulnerabilities such as erosion. First, you select the environmental conditions, starting with sea level rise. Strategies to protect the coast usually focus on physical barriers such as sea. You then have the choice to focus on long or short-term scenarios and in fair weather or extreme storm conditions. Next, you can select your area of focus from a map. We'll refine the focus to a small area off the coast of northern Germany in the Wadden Sea. It is also a carbon sink. Next, you can configure the nature-based solution, here by specifying the properties of the seagrass. You can choose the stem width and the height of the seagrass. Of the ocean application, for example, we can figure out the conditions and make. Moving on, you can choose the seagrass density for your selected area. And as the final step in configuring your vegetation, you can set a custom range of seagrass distribution from the shoreline out into deeper waters. Because of this customization, users can take a look at the impact of different vegetation conditions to find the best planting depths or densities. Once the setup is complete, you can submit your nature-based solution scenario with a single click. It's then compared to one without any vegetation so that its impact can be calculated. One of the results available in our application is being able to see the distribution of vegetation in the selected focus area. Seagrass meadows in our example are shown here in green. Another result we can see is the impact of vegetation on the wave heights near the coast. Areas with reduced wave heights are shown here in our example in blue. This has applications to the use of nature-based solutions for flood mitigation, since high waves are one cause of coastal flooding. Another result available to users is the impact of vegetation on coastal erosion. In our example, blue shows where there is less erosion taking place. Seagrass meadows reduce the wave heights near coastal areas, reducing erosion. This is applicable to projects such as West Coast as well. You then have the choice to focus on long or short-term scenarios. With the use of artificial intelligence, we can take this a step further, predicting the risk of coastal erosion in the future. This can help policymakers find high-priority areas of erosion risk for using nature-based solutions, and is used additionally in the Focus project. You can configure the nature-based solution. With this application, the ability to test nature-based solutions that are tailored to users' specific regional needs is groundbreaking. Decision makers will be more informed about using vegetation to reduce erosion risk and wave heights on the coast. This in turn helps reduce the cost of coastal protection for us all. This application benefits a wide range of users, from European governmental agencies and coastal zone managers who are protecting our coastlines from climate change, to national agencies securing the future of our nation's coasts, to citizen scientists working to restore coastal ecosystems. Nature-based solutions have the potential to impact decision-making for coastal protection at many different levels. This compared to one without any vegetation so that its impact can be calculated. One of the results available in our application is being able to. The Hydrodynamics and Data Assimilation team at Herion, KSD, is working on implementing the use of nature-based. Another result we can see is the impact of vegetation on the wave heights near the coast. Areas with reduced wave heights are shown here in our example in blue. This has applications to the use of nature-based solutions for flood mitigation, since high waves are
Just to
cause of
conclude my talk,
Another result available to users is the impact of vegetation.
which is AI for the ocean. The AI plays a crucial role
In our
for the
example, blue
developing
shows where
of
there
the
is less
digital
erosion taking
technology.
place.
Because
Seagrass
through
meadows reduce the wave
developing
heights
the
near coastal
artificial
areas, reducing erosion.
intelligence,
This is
we are
applicable to
able
projects
to
such as West Coast
improve
as
the
well.
analysis and the prediction of the ocean because we
With
produce a
the
big
use of
amount of
artificial
data, and
intelligence,
those
we can take
data
this a step
also
further,
can
predicting
be
the risk of coastal erosion
accessible.
in the future.
What is very
This can help
important is
policymakers find
that
high priority.
to the AI we can significantly enhance the
areas of
computational
erosion risk
efficiency
by
and
using nature-based
computational cost
solutions,
because
and
we
is
need
used
quicker
additionally in the
solution. For
focus group.
example, many use
With this
ChatGPT or
application,
any other
the ability to test
AI-driven
nature-based solutions that
platform,
are tailored
and
to
if you
users'
ask
specific
questions,
regional
you
needs
need
is
a very
groundbreaking.
quick solution.
Decision makers will be
And
more
this
informed about
is
using
why
vegetation to
AI
reduce
can
erosion
really
risk
enhance
and wave heights along the
reducing
coast.
computational
This in turn
efficiency.
helps reduce the
It
cost of
can
coastal
be used
protection for
for
residents.
improving the downscale accuracy because
This
many users
application
and
benefits a
stakeholders
wide
they are
range of users,
interested in what is happening in the coast, and here is where we
from
really lack
European governmental agencies
sufficient
and
high
coastal zone
resolution
managers
cost
who are protecting the
data,
coastlines
and
from climate
this is why
change,
AI can
to
also
national
be used
agencies
for
securing the future
providing
of our
the
nation's
easy
coast, to
solution.
citizen
And I
scientists
give you
working to
a
restore coastal
framework of
ecosystems.
example of how the
Nature-based
digital twin
solutions have the
technology,
potential to
which is
impact
AI driven,
decision-making for coastal
can be
protection at
used
many different
as
levels.
structural framework for coastal protection and adaptation. And in such a case, it can really support a real-time environment. Practitioners and decision makers, they can make their digital twin what if
The
scenarios
hydrodynamics data
before going
assimilation
to
team at
operation,
Avionics
before
KSU
planting
is working on
seagrass or
implementing the use of
before
nature.
deploying observational equipment. You can already
Impact
play
of
with the
vegetation on
digital.
wave heights near the coast.
This is why
Areas
it
with
helps
reduced
to
water
evaluate
loss are
nature-based
prioritized and
solution
improved.
digital strategies. And I the outlook,
Nature-based solutions are beyond mitigation.
sorry,
High waves and
that
drought
the
risk
AI
do
powered
not
digital twin technology,
another result
it
of
really
connecting users
offers the valuable opportunity for marine sustainability, but also for climate adaptation and for hazard mitigation all over the coast. Digital twin technology should be used for the whole world. It shouldn't be used only for selected countries. Here we are really targeting the global ocean, the one ocean, the one coast. This is why the continuous research into improving the AI and improving the machine learning technology together with the high resolution integrated modeling approach is very crucial. And this is why the link between the AI-driven models and the AI-driven digital together with the real-world decision making is very important to enhance the long-term coastal resilience. Thank you.
vegetation to reduce erosion risk and wave heights along the coast. This in turn helps reduce the cost of
It can
coastal
be used
protection for
for
residents.
improving the downscale accuracy because many
We
users
request
and
Dr. R.
stakeholders they are
Venkatesan to
interested in
facilitate the
what is
momentum to
happening in the
Dr.
coast,
Joanna
and
Stalina.
here's where we
From
really lack
European governmental agencies and
sufficient high
coastal zone
resolution
managers
cost
who are protecting the
data,
coastlines
and
from climate
this is why
change,
AI can
to
also be
national
used
agencies
for
securing the future
providing
of our
the
nation's
easy
coast, to
solution.
citizen
And I
scientists
give you
working to
a
restore coastal
framework of
ecosystems.
example of how the
Nature-based
digital twin
solutions have the
technology,
potential to
which is
impact
AI-driven,
decision-making for coastal
can be
protection at
used
many different
as
levels.
structural framework for coastal protection and adaptation. And in such a case, it can really support a real-time environment. Practitioners and decision makers, they can make their digital twin what if
The
scenarios
hydrodynamics data
before going
assimilation
to
team
operation.
Avionics
Before
KSU
planting
is working on
seagrass or
implementing the use of
before
nature.
deploying observational equipment, you can already play with the digital. This is why it helps to evaluate nature-based solution digital strategies. And I the outlook.
We request Ms. Priya to introduce Dr. Kakani Katija.
Technology. It really offers the valuable opportunity for marine
On behalf of the Department
for climate adaptation and for hazard
Electrical and Electronics Engineering, XRM Institute of Science and Technology, it is my great pleasure to introduce our distinguished speaker for today's session. We are privileged to welcome Dr. Kakani Katija, a renowned ocean focused bioengineer and a National Geographic Emerging Explorer whose multidisciplinary work bridges the field of aerospace, bioengineering, and marine technology. Dr. Katija began her academic journey with a bachelor's degree in aeronautics and astronautics from the University of Washington in 2004.
She went to earn on her master's degree in aeronautics in 2005, PhD in bioengineering in 2010 from the prestigious California Institute of Technology. She is currently serving as a principal engineer and investigator at the Monterey Bay Aquarium Research Institute, where her work focuses on developing innovative underwater technologies to enhance the observation and study of marine life. Her contributions include the development of advanced imaging and illumination tools such as TPIV and IRIS, as well as the use of artificial intelligence for automating visual data classification through FathomNet. She also integrates machine learning algorithms on robotic vehicles for missions involving cutting edge platforms like Mesobot and LRAUV. Dr. Khatija's visionary approach and groundbreaking innovations continue to shape the future of ocean exploration and marine science. Please join me in welcoming Dr. Kakani Khatija for this session.
I can hear you. Can you hear me? Perfect. I will share my screen for my slides. Hold on. I think you're sharing the wrong screen. Let's do this one.
We request Ms. Priya to introduce Dr. Kakani Khatija.
Do you see my full slides?
On behalf of the Department of Electrical and Electronics Engineering, SRM Institute of Science and Technology, it is my great pleasure to introduce our distinguished speaker for today's session.
Yeah,
We
I'm
are
trying to
privileged to
select the
welcome
appropriate
Dr. Kakani
screen, which I
Khatija, a
believe is this one.
renowned
And then you
ocean-focused
should
bioengineer
see
and a National Geographic Emerging
just the
Explorer
slides.
whose
That's correct.
multidisciplinary work bridges
Okay,
the field
good.
of aerospace,
Well, thank you so
bioengineering,
much for
and
your
marine
patience,
technology.
everybody.
Dr. Khatija began her
I'm
academic
very
journey
excited
with a
to be able
bachelor's
to
degree in
present
aeronautics
some of
and
our work.
astronautics from the
I
University of
really
Washington in
wish I was there
2004.
with you all. I would
She
love to
went
meet
to
you
earn
both
on
at some
her
point, but
master's degree in
you'll have to be
aeronautics in
sometime in the future
2005,
join
PhD
meeting. And today
in
there's a number of different
bioengineering in
projects that I've been
2010 from
involved
the
in. I
prestigious
really wanted to
California
highlight one in
Institute of
particular
Technology.
that we're,
She is currently
in the
serving as a
process
principal
of,
engineer and
having
investigator at the
released and
Monterey
also
Bay
applied. It's
Aquarium
called
Research
Fathomverse.
Institute, where
But
her work
I will also
focuses
share
on
with you
developing
kind of the vision
innovative
or the
underwater
goals of how
technologies
we're trying
to
to use
enhance the observation
AI
and study of
more
marine life.
broadly to
Her
help
contributions
identify and
include the
potentially discover
development
new
of
life in
advanced
the
imaging
ocean. But first, before I really get started,
and
you can
illumination tools
imagine
such as
that efforts like
TPIV
Fathomverse, and I'll
and
explain what that
IRIS,
all
as well
means,
as the use of
takes a lot
artificial
of people,
intelligence
a
for
lot of
automating
input,
visual data
and obviously a
classification
lot
through
of
FathomNet.
expertise.
She
And
also
so I'm really
integrates
grateful
machine learning
to
algorithms on
the
robotic
software
vehicles
engineers,
for
the
missions
mechanical engineers,
involving
the electrical
cutting-edge platforms
engineers,
like
the
Mesobot
marine
and
biologists, the
LRAUV. Dr.
taxonomists, and other
Khatija's
members of our
visionary
group that
approach
have
and
participated
groundbreaking
in some
innovations
capacity.
continue to shape the future
But
of
also I want to thank the variety of funding
ocean
agencies that have
exploration
supported a
and
lot of
marine
this work.
science. Please
Because
join
of
me in
course,
welcoming Dr. Kakani
this
Khatija
wouldn't
for this
exist
session.
without a lot of their input. And as what was said in my introduction about my bio, my background is interestingly not related to the ocean at all. It's actually related to space. In fact, I got my academic start in aerospace engineering, and the reason for that is I actually wanted to become an astronaut. I was always very enamored or excited by the idea that we could be, going into outer planets or outer space with the goal of discovering new life and potentially interacting with it, learning about it, and then bringing that information back home. And so I thought at the time when I started my academic career that becoming an aerospace engineering would get me very close to becoming an astronaut. And it wasn't until graduate school where, let's say, my appetite had changed, where instead of focusing for the search for life in outer space, I soon learned that the ocean is teeming with life that we're only just starting to understand. And what you see here is not a star field. This is actually what the Monterey Bay looks like at about 400 meters deep. And so, while we've so far been unsuccessful at finding life outside of our planet, the oceans are teeming with life that we know very, very little. And so, for me, anyways, this is a big, important jumping off point. I started out in graduate school, focused primarily on scuba diving. I had some opportunities to work at other oceanographic institutions as a postdoc and also as a researcher. And, finally now I'm working with more advanced robotics, imaging systems, etc. And so the problems that really drive my interests, as well as the things that we work on within my lab or our group, it's called the Bioinspiration Lab, is actually inspired by plots that you might see like this one. So this is a plot showing where you might find biodiversity occurrence data, and by occurrence data that means whether or not an animal or an object was observed at that location. And this is data that's pulled from the Global Biodiversity Information Facility, so one of the big data aggregators for biodiversity information. And when you see plots like this, and often when people talk about plots like this, they tend to focus on the really bright red spots, right? Because these are areas that are locations where we have lots and lots of biodiversity data or occurrence data. And then researchers will also focus on the areas of the map where we don't have that data, but largely focus on terrestrial locations. So you see in green, obviously parts of the Arctic, northern part of Africa, as well as the further reaches of northern parts of Asia, and of course Antarctica. And while I think that also reflects kind of our observation bias, right? The fact that we tend to focus on what's going on in terrestrial environments. If you look closely at this map, the biggest gaps are actually found in the ocean. So those big areas of blue without any data, those are locations where we don't have biodiversity information or biological observations. And so if you take this information though, and then you start to ask the question of, it's not just a single observation in time for all time, which is kind of what you're seeing in this plot. But let's focus on the places where we're able to have kind of consistent observations of life, let's say repeated. And as you know, like repeated observations are really important because that tells us something about how a place might change or how biodiversity might change in a location over time, due to environmental impacts, due to human activities. And so this plot here, this is from a paper by Aaron Satterthwaite and a number of different authors. They looked at, again, biodiversity data available in these big data sets, and they isolated data where we would have repeat biological observations. So basically places where we have these observations for longer than 5 years. I want to highlight though that they've also focused on, one, excluding remote sensing, right? Because observations from satellites do give us a really broad swath of observations, but unfortunately those observations tend to be really close to the surface, which is actually what this plot is also showing. It's only showing biological observations that are repeated near the surface about as deep as 5 meters. And what they showed, as you can see on this map, the colors indicate places where we have these repeat observations. They showed that about 7% of the ocean surface area is covered by long-term biological observations. Of course, we know that the ocean isn't just a surface, right? It's a massive volume representing a vast majority of the livable volume on our planet. And then on top of that, not only do we have these obvious spatial and temporal observational gaps, we also have just a general lack of understanding of what is in the ocean. Researchers estimate anywhere from 30 to 60% of life in the ocean is undescribed or unknown to science. So, how do we have any chance or any hope of filling all of these observational gaps in a time of rapid change, right? The fact is, the ocean is changing really quickly, thanks to climate change and other activities. And so our inability to make these observations rapidly or broadly means we're also not informed on how these changes are impacting these ecosystems and how might we, rise to the challenge of trying to observe them and preserve them. And so it's these questions that really drive the activities of our group, the Bioexploration Lab. And so the way we tackle this and filling our observational gaps of biology in the ocean is by focusing on the things on the left. That is the building out state-of-the-art instrumentation, or utilizing or building innovative observation platforms, but then also creating mechanisms for the community more broadly to access novel study systems. And the reason why we're called Bioexploration Lab is because what we're hoping is that if we can combine all three of these things, one day we can then provide quantitative information about biological systems that might one day inform things like deep sea bio-inspired design. So think about underwater robots or vehicles or coaches that are inspired by biological systems. And so far we've been really fortunate. I just wanted to share a couple of examples of things that we've just been able to do so far. And I think it was mentioned in the intro, there's a number of imaging systems that we've developed. DPIV, which is a laser-based imaging system. IRIS, which is a planoptic or light field imaging system that enables quantitative 3D measurements. And then we also more recently have a multi-camera payload that can be integrated on autonomous mobile vehicles called Titan. Examples of innovative platforms that we've used and also helped develop include the long-range autonomous underwater vehicle, ROVs, as well as a mini ROV that allows us to deploy our systems and approaches on ships of opportunity. And then last but not least is Mesobot, which is a vehicle that was specifically designed to study animals in water. But more recently, I've been really excited by this concept of access. Like, how do we provide access to novel study systems in the ocean when it's so hard to get there, particularly in the deep sea? And so one of the ways we've been thinking about how we can do this is through data. How can we make data, really accessible so that almost anyone can participate in, but also be inspired by the biological systems that we study in the ocean. And so what I'm going to focus on today is actually talking about these particular activities. These are also probably most relevant to this conference, and that is the FathomNet program, as well as the Fathom First Aid. And the reason why, at least in my mind, these things are so important is because, remember I talked about these observational gaps that we're facing in biological studies in the ocean. And the research community is kind of in a race to deploy a variety of different technologies to fill those gaps. Biological observations are conducted in many different ways. There's things like environmental DNA. There's things like acoustics or sound, measuring sound underwater so that you can perhaps identify what something is that you hear. But I would say perhaps more popularly is the use of imaging. And imaging, unlike those other two approaches I mentioned, is the most direct way to make an observation of an animal. And in fact, imaging is often required to validate those other two of theory. You need to see what force the also for to identify it, or you need to see what the animal is whose DNA, right, is what you're actually measuring. And so this approach for imaging is so important and so very powerful. And while we are trying to fill these observational gaps, we are using all different types of imaging systems, all different types of platforms, be it these really expensive, massive robots or even scuba divers. And our problem, right, is the collection of all of this information and doing it at such a rapid pace without really taking the time to process all of it or really make it available broadly so that we can be answering, broad global questions about biological disease. So keep that in mind. The other challenge, right, is to convert all of this information that we're collecting into something that's useful, right? This is an example of a video that's been collected by one of our underwater robots. And what you'll notice just looking at all of this video is that you can see different types of animals. Experts can identify those animals down to species level. You can count these animals. You can count all the different species. You can also note relationships, let's say, between them, but also relationships between the substrates that they might be inhabiting. And so all of that information, right, is contained in pixel data, and how then do you convert it to something that has some action, right? Counts of animals, names of animals. And so, I'm very fortunate at Ari. We have a video lab, which is a group of 6 or 7 visual taxonomy experts whose job it is to convert this data manually from pixels to actual data sets. But that's not scalable, nor does everybody have expertise of being able to look at an image and identify something else. And so this is where, I argue, and a number of my collaborators argue, that we've got to come up with a more scalable way. And, as we know and we've seen throughout the years with the developments in computer vision, artificial intelligence, that might be an approach that's very powerful that we can take advantage of. But as I think everybody knows here, training algorithms, deploying algorithms, they work relatively well. Of course, there are many instances where these algorithms don't work, right? Let's say data are out of distribution or whatever. And so the real challenge is, to not only train these algorithms and deploy them, but also to ensure different ways that we can have humans in the loop, either improving those models, correcting those models, verifying those models, so that we can get more quickly to annotated data out, right? That is really the crux of the challenge that we're facing as a community. And so what we've decided to do was then focus on how do we inject human verification in a really meaningful and effective way, especially when we think about the broad range of individuals that could be participating in this human verification process that might have different expertise or different varying amounts of time, or even, numbers of these individuals. So, like, for example, there aren't a lot of computer vision experts in the world who are interested in ocean-based problems. There aren't a lot of, taxonomists or marine scientists that have the time to review all of this visual data. But there's actually a lot of enthusiasts in the world. People who go to aquariums, people who watch a lot of nature documentaries, who've acquired knowledge about ocean life in some way. And so how do we marry this broad spectrum of individuals into this problem of providing human verification at large scales? And so what we then did was we conducted a very long user-centered design study. It took about 9 months. And what we also learned or determined was that we couldn't build like a one-size-fits-all solution for this entire audience. And so instead focused on particular solutions that would address the needs or the concerns of these particular groups. And so what we found, or what we learned, and what we started with was the FathomNet database. And I have more information about that in the slide. But really, the idea of this is that this is something for experts, expert taxonomists, expert marine scientists, and also computer scientists looking for new applications or data sets that they can then test their state-of-the-art algorithms on. And the idea is that the Fathom database represents a global image and machine learning model repository where people can upload and get their visual data that is labeled, posted, as well as the machine learning models that we can then train but also share more broadly. It's publicly available and serves as a taxonomic expertise aggregator. And we entered into an agreement with NOAA, the National Oceanic and Atmospheric Administration, to host submit data to the data set for up to 75 years from all over the world. So, in fact, I believe contributions from India are accepted and hosted by NOAA. The other thing I want to highlight too is that we've been, for the last 3 years, including this year, we've been hosting Fathom It Kaggle competitions. These are data competitions that invite computer vision experts or researchers to work on novel problems that we're focused on in the ocean. Last year we focused on novel category discovery. This year we're focused on hierarchical classification. But feel free to visit that website and check out the data set. The next thing that we focused a lot on is called the Fathom portal, and you can think of this as really just a platform that provides access to machine learning data pipelines. Most of the people we've spoken with in brain science, have this need to process their information, but they don't obviously have a computer science degree that can then be used to cobble together a bunch of different software solutions to address their problems. And so the intention of the portal is that we can, provide including and hosting of visual data where researchers can create public or private repositories using that data. And then they can also select and train, deploy their machine learning models. But really the most important thing is to get annotations from their data and ensure that those annotations are useful to them, but also can be exported to these global data sets like OVIS or GBIF, as I mentioned before, and even the Fathom database. And so we did launch this platform in September of last year. So if that's something of interest, please reach out and check out that website. And then the last thing I wanted to talk about, which I'm very excited about, is Fathomverse. And Fathomverse is inspired by a lot of the work that's already been happening within the green imaging community. There's been a lot of efforts for community science or citizen science to try and get people from a lot of different backgrounds to be participating. And so we went a whole step further and focused on video gaming in order to do this. And an approach that we're taking around talking about the game, or at least sharing this approach, is also inspired by Dr. Jyotika Kumani. She was formerly with X Prize. She's now the director of Ocean Institute, and she wrote an article in 2017 that talks about the differences that the space community and the ocean communities engage public audiences. Because, as you know, if our goal is to build out a game or a platform that engages the public, we want to make sure we're doing that effectively. And also, bring them in the long haul. And so what she did in the article was contrast the way that we talk about space or ocean with the public audience. That includes messaging tone. In the ocean, it tends to be really negative. The narrative focuses tend to be ideas-based, like climate change, which is unfortunately really difficult for the general public to understand. The messaging content tends to reflect the community structure in the ocean because there's hundreds of different governments, NGO, advocacy, education organizations that all have their own agenda. And so somebody from outside that community is often confused about what is actually important. The other thing is the narrative outcomes in the ocean tend to be really doom and gloom. there's a really good reason for it, so I don't blame them for this. But if we can lean in on the things that have worked really well for the space community, like positive messaging tone, talking through a narrative that's mission-based or mission-focused, like discovering all life in the ocean, creating a mechanism for us to celebrate collective human achievement, being unified and cross-promotional. The idea is that we're speaking as a community together, but directly interacting with the Fathomverse community, and then also presenting narrative outcomes that are really forward-looking. The idea that we are working together to discover all life in the ocean. And so it's this approach that we have adopted for Fathomverse. The idea here is that we are crowdsourcing annotations through gaming, and the audience is high school aged, age 15 and up. And then the idea here is we want to make it accessible. So it's a mobile device app that can be used on your iOS or Android device. And then we're very focused on design pillars. So what are the foundations through which we are building this game? And the idea is that we want to really lean into exploration, like inviting players to explore with us. We want to make moments of blissful productivity. The idea that labeling or annotating data can often be boring, but we can make it fun and accessible, but also, allow people to spend some time instead of relying on social media, potentially doing something productive. We also wanted to make sure that this was really casual. This isn't something that you're going to dedicate hours have time to, but it's something you can pick up really quickly and within 5 minutes make a meaningful contribution. And then we also wanted to keep it really real. We didn't want a fake narrative. We just wanted to invite people to join us on this inspiring mission, discovering all life in the ocean. And I just wanted to say that we are so fortunate for the data contributions that we've been able to receive so far. That includes Schmidt Ocean Institute, NOAA's Office of Exploration and Research, Ocean Networks Canada, Ocean Observatories Initiative, Ocean Exploration Trust, and of course my institution. And if this is something your institutions or groups would be interested in, please reach out to me, and I'm happy to chat. But first, I need to switch to another screen because I want to share with you all the trailer for the game that we launched. I'll share this.
But also can be exported to global formats like Ovis, Archiva, as I mentioned before, and even the Fathom technologies. And so we did launch this platform in September of last year. So if that's something of interest, please reach out and check out that website. And then the last thing I wanted to talk about, which I'm very excited about, is Fathomverse. And Fathomverse is inspired by a lot of the work that's already been happening within the green imaging community. There's been a lot of efforts for community science or citizen science to try and get people from a lot of different backgrounds to be participating. And so we went a whole step further and focused on video gaming in order to do this. And this an approach that we're taking around
Screen, and I hope I can get this to work.
talking about the game, or at least sharing
Click play.
approach is also inspired by Dr. Joe's.
Can you tell me what you're seeing?
She was formerly the X Prize, she's now the director of
So
Institute. And she wrote an article in 2017 that talks about the differences that
Is it the full screen?
the space community and the ocean communities engage public audiences, because
So you see the full screen?
as you know, if our goal is to build out a game or a platform
It's blank.
that engages public, we want to make sure we're doing that effectively, and also bring them in. And so what she did in the article was contrast.
Let's present something else.
Space
Entire screen.
public audience, that have messaging tone. In the ocean, it tends to be really negative.
Now you're seeing a screen?
Ideas based, like climate change, which is unfortunately really difficult for nature in general.
Right. Full screen.
The messaging content.
Perfect. Okay, so what I'm showing you right now, I mean, while you saw the lovely trailer and everything, that tends to get a lot of focus. I actually want to spend some time talking about what's happening on the back end. And so all of this is actually facilitated by the game back end, but also a content management system that we built called, for short, the CMS. And this video just showed you the application programming interface, or the API descriptive docs, that allows us to integrate data from a lot of different sources, do a bunch of logic to, use the data, but also convert it into something helpful, but then, of course, the game backend. And so the way this works as the content management system is essentially what is the connector between all of these different things. The idea being data can be coming to the content management system either from the portal or from contributors that are giving data directly. Those data are unlabeled data, so that those can be videos that we convert into images and ROIs. And then we also have data coming from the .NET database, which are expertly labeled data, right? And so the way the CMS works is it takes in those different data sources and breaks up that data to create what we call unlabeled play contexts. So they're a combination of unlabeled and labeled data that a game player will then look at and label with every die for every activity within the game. Once they label that play context, the CMS then takes all that information, aggregates it, looks at all these player annotations, and then compares how well the game players did on the expertly labeled data coming from the .NET database. And what then we do is calculate player reputation scores, accuracy, precision, recall, F1, on per animal mission. And so we can then take those player reputation scores, inject them into a consensus protocol, and then come up with labeled data that we can then share with our contributors or back with the .NET database, right? So the idea is we can grow the data that's available to our community to then train models and then repeat this process over again. And so that is how the content management system works, or an example of how it works. It also is storing a lot of other information. But the big important piece to this is that the content management system allows us to grow the game with time, depending on needs. And so what you see here on the left is the different animal missions where game players are searching for particular animal groups within the imagery of the game. These missions, we started with 45. I believe now we have over 60. We have different awards that game players can unlock based on the different points that they contribute as they play the game. And then also something we're thinking about over time is we have these different mini games which serve as different data interactions. So while we've started with application, we're also now looking at localization. And right now we're focused on imagery, but you could think of in the long term also incorporating sound and other data types that, again, will grow these data sets that we need for us to share with you. And so just quickly, Metaverse represents about a $1 million system. The system launched in the first quarter of the first. We have more than 33,000 players now, representing 175 different countries, and they have now generated more than 17 million annotations. I also want to say we've rolled over more than 100,000 previously unlabeled images, have reached consensus, and represent about 30% of the number of images that currently have in the .NET database. And those are all contributions from enthusiasts playing the game. And we just launched the second version of the game a couple weeks ago, March 26th. And there we incorporated localization, in-app messaging, and badges. And so this is something I'm really excited about because, the fact that we're able to engage a very large audience and also teach them not only about Ocean Life, but also how artificial intelligence works, how it doesn't work, and how we can work together to improve it. And so then the idea is that over time we'll be able to have different numbers of verification or contributions from these different platforms so that we can build towards human verification at scale so that we can get annotated data out anywhere we generate data and also deploy these models. And so this is, an example of, that same video I showed earlier, model that was trained on data generated within the Monterey Bay, but can also be accessed using the data set. And just want to say, this looks very impressive. It's not perfect, but of course, with humans in the loop, we can improve these models so that we can be deploying these instruments, reviewing, analyzing data, and being able to identify all life in the ocean. In addition, the idea is that, using these kinds of approaches or these models, we can also move from using or relying on really expensive, really time-consuming and resource-consuming platforms for observations to autonomous systems that can do very similar tasks. And so that's, I think, a very exciting aspect of a lot of this work. It's like once we have kind of this data infrastructure built out and collaborations with computer scientists, we're then going to be able to really push the envelope in terms of how we can do observations at scale using autonomous systems. So with that, I'm happy to take any questions you might have about anything I shared with you today.
And this video just showed you the application programming interface or the docs, that allows us to integrate data from a lot of different sources, do a bunch of log to, use the data, but also convert it into something helpful, but then of course the game backend. And so the way this works as the content management system is essentially what is the connector between all of these different things. The idea being the data can be coming to the content management system either from the portal or from contributors that are giving data directly. Those data are unlabeled data, so that those could be videos that we can convert into images and ROIs.
Thank you, Dr. Gagani Venkat here.
And then we also have
I don't
data
know
from
if you see me.
database.
Thanks a lot for sparing your time and late night for you for really state of art new technology for all of us. We are flabbergasted to see that such a technology is happening. I'm sure that these ideas will come to students here and they will start working. And I'm joining with Nicole here. We both are close friends of Dr. Jyotika, and she introduced me to you, and we are here and shared this interesting topic.